In this video, we are going to discuss Bellman Ford algorithm to find out single source shortest path. Bellman Ford algorithm help us find the shortest path from a source vertex to all other vertices of a weighted graph. Let's say this is the weighted graph we have been given, and each edge in this graph is having a weight, and this weight is the length of the path. Now we have to find out the shortest path from the source vertex to all the other vertices. We can also use Dijkstra algorithm to deal with such a problem, but Dijkstra algorithm cannot work well with graphs having negative weights. And here see we are having negative weights. So we should go for Bellman Ford. And Bellman Ford uses dynamic programming, unlike Dijkstra that uses greedy algorithm. Alright, let's go ahead and see how it works. So we apply this algorithm when we have single source. So let's say that the source where we're going to start from is A. So first we overestimate the length of paths from starting vertex to all the other vertices. And let's say all the other vertices are infinity distance apart from starting vertex A. And obviously the distance of source from itself is 0. And now we're gonna iteratively relax these estimates by finding new paths that are shorter than the previous estimations. And how are we gonna do this? So we're gonna pick two connected vertices, let's say u and v, having distance du and v having distance dv, and the cost to reach from u to v is cost uv. Then if the addition of distance of u and the cost of uv is smaller than dv, that is smaller than the distance of v, then distance of v can be relaxed or updated as the sum. So this we're going to do for all the pairs. And we're not going to do this just once, we're going to do this for all the pairs repeatedly. So if we have n vertices, then we have to do it exactly for n minus 1 times. And by doing this repeatedly for all the vertices, we can guarantee that the result is optimized. So let's have all the pairs here. So we have AB, we have AF, we have AD, we have BC, CE, DE, FB, FC, and FE. So now let's start the iteration. First pair is AB. See the value at B, it is infinity, and at A we are having 0 and the cost is 8. So when we add 0 and 8, the sum is smaller than infinity. So the distance of B can be updated as 0 plus 8, that is 8. Next pair is AF. Again see the distance at A is 0 and the distance at F is infinity. And the cost is 5. So when we add 0 to 5, it is smaller than infinity. So we can update DF. Next pair is AD. Again 0 plus 3 is smaller than infinity. We're going to update DF as 3. Now next pair we have is BC. B is having value 8 and the cost is 6, which is 14, and it is smaller than infinity. So let's update DC. The same we're gonna do for all the other pairs. The next pair is CE. So at E we are having infinity and 14 plus 4 is 18. So we're gonna replace this infinity with 18. Now next pair is DE. At E we are having 18. Now we're gonna relax this edge as 3 minus 1 is 2. So we're gonna update it to 2. Next is FB. At B we are having 8 and the value of F is 5 and the weight is minus 4. So 5 minus 4 is 1. So we're going to replace 8 with 1. Next is FC. At C we are having 14 and 5 minus 1 is 4. So again we're going to replace it with 4. Now the next FE. Here at E we are having 2 and 5 minus 3 is also 2, so we're gonna keep this 2. So at the end of this iteration we're gonna have these values. But this was the first iteration. We have to make n minus 1, 6 minus 1, that is 5 iteration. So again we're gonna do the same with these sequence of pairs. Again we have to start from the first pair AB and then we have to go till FE. So this will be the second iteration and then the third, fourth, and then the last iteration, fifth one. So we're going to do this for a total of 5 times and then finally we're going to get the solution at the end of fifth iteration. In many cases you may get the solution in initial iterations as we got the solution in the first iteration, but there can be cases that may give you the solution in the last iteration. So we always have to go for n minus 1 times because the optimal solution is guaranteed only when we iterate n minus 1 times. So this is how this algorithm works, and there is one drawback of Bellman Ford, that it cannot work with negative cycles. What is a negative cycle? See this, these vertices are forming a cycle, right? So when you sum all the weights for these vertices, you get a negative number. And that's why it is called a negative cycle. So if there is any negative cycle in the graph, then Bellman Ford algorithm will not work for that.